All right, welcome to today's Rising Tide Foundation lecture. We've got a guest in town from Bogota, Colombia, in the form of Dr. John Plaice, who is occupying my typical seat in the study. So today, this is going to be a fun presentation because we've already had a few presentations dealing with the political ramifications of holding on to bad sets of ideas, especially regarding the science of economics, the science of energy policy, what are competent, what are incompetent concepts of thinking about energy, its relationship to human life, supporting human life, and how that applies to different systems of governance. If we think of governance also as a political as a type of technology that can degenerate or be improved upon as well, based upon certain concepts, ideas that are truthful or fallacious regarding, natural law as a standard. So that's been fun as the last few weeks are concerned. A lot of people today hear the words trust the science a lot. Stop thinking for yourself, trust the science. The science says this. In fact, maybe thinking for yourself or trying to do your own research on whatever is dangerous. And again, you could fill in the blank of what that whatever might be. But this causes problems. And so the question is, like, whose science, right? Are all ideas of science created equal? Well, I think everyone who has come onto this presentation today has discovered to varying degrees that no, there's not one thing that we should all worship called science that everyone agrees on. There are many battles, many clashes throughout the centuries, if not longer, over the question of method. So John has done some really fun research. I'm really looking forward to this on the question of certain battles that took place that have been really obscured from common knowledge. For most students of history, especially the history of science, they're not easily privy to these clashes. So I'm very happy to have John Plaice here introduce the 19th century and some of the universal battles over this idea. And like usual, once the main presentation is done, just pop your name, or as the presentation is going. For all of the names that I see in the chat box, I will call upon you in queue to ask John a question, share a thought. If you want me to ask the thought for you or the question, simply write it out very succinctly, and I will do so. Otherwise, John, the stage is yours.
Thank you very much, Matt. It's a pleasure to be here. It's a bit cloudy and it's very different from Bogota, whether we see the sun all the time, except when it's raining. Rains every day, of course, but that's so I'm going to talk about something that I've held to heart for quite a long time, but only recently have I, how shall I say it, seriously studied the question. So I'll begin by sharing my screen. Do you see it?
Yes.
Okay. So the title is The Replacement of Continental Physics in the 19th Century. So just to be sure, the continent in question is Europe, or in particularly Western Europe. And the two most important countries that we're talking about, at least in the 19th century, are, of course, France and Germany. Germany, of course, only became a united entity in the second half of the 19th century under Bismarck. I have a Substack, and if you're not already subscribed, I encourage you to do so. I write my thoughts there, and some people find it interesting. And I have some people from 40 countries, so it's quite interesting there. So the question, so the first, hold on, there must be some kind of, full screen on this. No, that's not it. Sorry.
It looks like you have a PDF there, John. I don't know if there's a full screen.
Yeah, there it is. There it is. Sorry, got it. Oh. Okay, so the why this talk? Well, first of all, it should be understood that I'm not a professional physicist. I worked in computer science my entire life. I can read scientific papers, I can follow the technical aspects. With work, I can follow the mathematics. So I think I have the ability to actually study and read physics, but I'm not a professional physicist. One thing I do find is that modern physics is hard to understand. I don't really understand the concepts. And furthermore, if I go to the local bookstore, whether it's in Bogota or here or in New York, or I go to the science section and there's tons of stuff about general relativity and quantum mechanics and maybe molecular biology and telling us about this and that and the other thing. And you find out that two of the most famous theoretical concepts are general relativity and quantum mechanics, and they're not compatible. And yet they've been around for over a century. It's like, there's problems here. Okay, so let's work backwards. General relativity depends on special relativity, and special relativity is ultimately based on James Clerk Maxwell's electrodynamics. I think Einstein said he didn't stand on the shoulders of giants, he stood on the shoulders of Maxwell. Quantum mechanics, well, that's the work that comes from the discoveries of Max Planck in the early 20th century, but that was already assuming the black body radiation, the results of I forget whom. I can't remember. I'm sorry. And then you get a concept called heat death. And where does heat death come from? Well, heat death, we're told that this comes from the second law of thermodynamics. It's like, so all this stuff sounds, to me at least, fairly weird or not fully comprehensible. But it all seems to ultimately depend on ideas that appeared during the approximate period 1850, 1870. So what happened during that period? Now, for those of you who study geopolitics, you had the US Civil War, you had the Japanese Civil War, you had the Indian Mutiny, you had the Crimean War. You had the invasion of Vietnam for the French, or Indochina, I should say. So at the geopolitical level, there's lots of stuff happening. You had the unification of Germany. But lots of stuff happened in science as well, and that's what I'm going to focus on. But let's first take a step backwards to the glory period of the early École Polytechnique in Paris. So what I'm going to present is that there were two productive research programs at the beginning of the 19th century, and I'm going to present these, or quick results. And then I'm going to move on to how, starting approximately the 1850s, these were replaced quite rapidly by new research programs. So the first productive research program is the luminiferous ether. So an ether is some incredibly fine particles, far smaller than our atoms and our electrons, and supposedly under which that's the medium through which light travels. Luminiferous is the adjective for light, of course. And the first person we associate with that idea is Christian Huygens. So he was one of the most brilliant scientists of the 17th century, both experimentalist as well as theoretician. And today we associate him with the wave theory of light. He's also the inventor of the pendulum clock. He was the first person to write about the Saturnian rings as some kind of disk. And he also solved the catenary problem. For those who are interested in Leibniz, he is also the one who taught the Leibniz mathematics. So he was some brilliant person. And already, I think it was already as a very young man, he had more or less solved the catenary problem. So let's take a quote of his. The second mode then of explaining transparency, and one which appears more probably true, is by saying that the waves of light are carried on in the ethereal matter, which continuously occupies the interstices or pores of transparent bodies. For since it passes through them continuously and freely, it follows that they are always full of it. And one may even show that these interstices occupy much more space than the coherent particles which constitute the bodies. So Christian Huygens is taking an idea of Descartes, which was there's 3 levels of matter, each successively finer. But he developed it, and he didn't insist that there is absolutely no void between the particles, but he did insist that these incredibly fine particles of ethereal matter, they're flowing through the big gaping holes that happen to be between the larger particles that make up, let's call it corporeal matter. Now, Huygens' idea wasn't really taken up. So, because at the time, very soon afterwards, Newton came up with he wrote his optics, and that was based on more of a corporeal or anatomistic model of light. Nevertheless, at the beginning of the 19th century, the British polymath Thomas Young did some interesting experiments, developed the interference experiment. That's where you have 2 sources of waves. So you have a source of waves in say in water, and you put it through and you have two holes in some wall, and you see an interference pattern on the second wall behind it. The same thing takes place with light. He also discovered that on the edge of shadows there are fringes of color. Now so he also talked about the luminiferous ether. A luminiferous ether pervades the universe. This idea of pervasion is really interesting. In other words, it flows inside the particles, rare and elastic in a high degree. Undulations are excited in this ether whenever a body becomes luminous. All material bodies have an attraction for the ethereal medium by means of which it is accumulated within their substance, and for a small substance around them in a state of greater density, but not of greater elasticity. Okay, the exact details of what's being read isn't crucial for the understanding of this talk. What's crucial is what's underlined in the various quotations that I am reading. Thomas Young is soon followed by Augustin Jean Fresnel, who truly developed the wave theory of light. Now, he proposed that light is a transverse wave in the ether. He was able to explain diffraction, he was able to explain polarization, and he's also the inventor of the catadioptric Fresnel lens, which is used, or was used, all over the world to build Fresnel lighthouses. So you have these sort of stepped lenses, the old lighthouses, that all comes from Fresnel. So what did Fresnel say? In the first section of this memoir, I have shown that the corpuscular theory, so that's Newton's, and even the principle of interference, when applied only to direct rays and to rays reflected or inflected at the very edge of the opaque screen, is incompetent to explain the phenomena of diffraction. I now propose to show that we may find a satisfactory explanation and a general theory in terms of waves without recourse to any auxiliary hypothesis by basing everything upon the principle of Huygens and upon that of interference, both of which are inferences from the fundamental hypothesis. Now, it's important to understand that Fresnel, when he made these presentations to the Académie des Sciences, got a standing ovation even from diehard Newtonists or diehard Newtonians like Pierre-Simon Laplace. Even the diehard Newtonians were convinced by the quality of his work. So this is one highly successful research program, the Luminiferous Ether. The second productive research program is completely opposite in nature. It presupposes action at a distance. Now, the person we normally associate with the initiation of this program is Isaac Newton himself. So Isaac Newton is best known for his 3 laws of motion, the first 2 which are essentially talking about inertia, and his law of universal gravitation. Now, of the laws of motion, the 3rd law is really important and will be important. It will play a crucial role in what follows. For every action, there is an equal and opposite reaction. So if you accept these laws, you should judge a theory by its ability to respect the 3rd law. In other words, the force that comes from, say, particle A upon particle B, is it identical but negative in direction to the force of particle B upon particle A? Now, I'm going to be showing some equations. The exact content of the equations is not important. It's the structure of the equations, which can be recognized visually. So this is the way we understand Newton's law of universal gravitation today. I don't think that's how Newton wrote it down, okay? So we have a force with a direction, and we have some kind of constant multiplied by something from the first entity, or in this case, the first mass, the second mass, the direction from the first particle to the second particle, over the square of the distance between the 2 particles, all right? So this structure is going to be replicated by successive researchers. So if we move on to Coulomb, who is the one who did all sorts of experiments and studied electrostatics, we find a very similarly looking equation. It's just that the constant is now different. And we're no longer talking about masses, we're talking about electric charges, Q1 and Q2. But you still have this thing here. You still have this r hat over r squared. In other words, that straight line between the 2 charges and the distance between, and the inverse square of the distance between the 2 particles is still there, all right? And Coulomb also came up with a similar equation for magnetic poles. And it's exactly the same structure. Here is capital Q1 and capital Q2. So these are the magnetic poles, but you still get this r hat over r squared. Now, of course, the constants change and the units change. The units of the constants change. That's fine, but it's the general structure which is essentially the same. This mu naught is called the magnetic constant, and if we go to the previous equation, we had epsilon naught, which is called the electric constant. They will reappear. So Coulomb worked on electrostatics. Coulomb was followed by Ampere. Now, Ampere was a very good friend of Fresnel. In fact, Fresnel lived in Ampere's house. And he was able to show that 2 parallel wires carrying electric currents attract or repel each other. And Ørsted came up with this experiment, and Ampere was able to fully explain it without any use of magnetic fields. That Ampere would have been scandalized without any discussion of magnetic fields. Now, Ampere is sort of like the Tycho Brahe, the Johannes Kepler, and Isaac Newton all wrapped into one for electricity. So he did the experiments, he did the calculations, and ultimately he came up with the laws. So his force law, not to be confused with what's called his circuital law, which was never Ampere's, is a bit more complicated than what we previously saw with Coulomb and with Newton. But you still get this, idea of the product of capital I1 and capital I2. In this case, the capital I's are the current intensities. And now you get some new body on the right. And this is taking into account now, remember, this is a force law not between particles, but rather between electrical circuits. And so alpha and beta and gamma are angles. And the angles in question are the angle from one current with respect to the straight line connecting the two current elements. The second is the angle of the other current with respect to the straight line connecting the two current elements. And the third one is the angle between the two currents. Okay. And so it's important to remember that these are not with respect to particles, these are with respect to electrical elements. So all of this is based on action at the distance. There's no assumption of any kind of medium or anything between the two entities that are attracted or repelled by each other. And then the successor in the world of electricity of Ampere is Wilhelm Edward Weber, who collaborated many years with Carl Gauss, and who co-invented the telegraph in 1833. He wrote 8 treatises on electricity, and he came up initially in the 1850s, 60 years before Rutherford did his gold leaf experiment demonstrating the existence of the nucleus of the atom. 60 years, 6 whole decades at a time of revolutionary discovery every year. And so he was an absolutely brilliant individual. So he came up with a force law, not between current elements, but between charged particles. Notice the little q1 and little q2. These are the same charges of Coulomb's force law. It's just that to the right, what's in the large round parentheses, we now have 3 terms, while before there was only one, which corresponds to the 1. This is essentially Coulomb's law if you ignore the minus r dot squared over 2c squared and the r double dot over c squared. So what is c? C turns out to be the speed of light. And the speed of light happens to be 1 over the square root of mu naught epsilon naught. Mu naught, remember, was the magnetic constant, and epsilon naught was the electric constant. So these things reappear. But it has a similar structure to Coulomb's law. So what's neat about it is Weber's force law generalizes Coulomb's electric law. So above it is the upper equation is Coulomb's electric law. And you see below it, it's simply that Weber's force law is a generalization. It talks about what happens taking into account the relative velocities of the 2 particles. That's what the minus r dot squared over 2c squared is. And the relative accelerations of the 2 particles. That's the r double dot, the acceleration. But furthermore, Ampere's force law can be derived from Weber's force law. So in other words, Ampere's force law, which was between current elements, can be derived from Weber's force law when you consider an electric current made up of moving electric charges. That's pretty neat. But Weber goes even beyond that. Weber's program was truly astonishing. Sorry, I was looking for the radiation. That was Kirchhoff. Okay. So 1846, Weber comes up with his force law. By 1852, he has an initial planetary model of the atom with negative charges rotating around positive charges. 1855, Weber and Kohlrausch, they do the first measurement of the speed of light. Kirchhoff and Weber independently derive the telegraph equation. And during the 1870s, Weber came up with his mature planetary model of the atom with precession of the perihelion of the negative charge. Mind-boggling. And at close distances, the mutual repulsion of positive charges becomes attraction. Now, with the data that was later available at the beginning of the 20th century, the calculations would give a nucleus of 10 to the minus 15 meters, which happens to be the exact diameter of the nucleus of atoms. And Weber never rejected the idea of the ether. He postulated that it consisted of very fine charged particles. So you'd think, okay, we have these two highly successful, but at least on the surface, apparently opposed research programs, and both are highly successful. So how should we go forward? Well, we should go forward by seeing perhaps there's some form of unity whereby what appears to be at one level, for example, action at the distance, if we pull out our ether microscope, we're doing a thought experiment, of course, then we could explain many of these things through some lower stuff. Is this what happened? No, this is not what happened. Something else took place. History was rewritten. Oh, we've seen this before in other disciplines. It happens in all disciplines. So this is the way history is understood when you study science in your typical high school or early university. So James Clerk Maxwell, Clerk Maxwell is actually the full family name. He wrote on Faraday's lines of force. So he took the lines of force of Michael Faraday and wrote a paper about it. Measurement of speed of light by James Clerk Maxwell. Oh, 7 years after it was estimated by Weber. And then in 1873, the treatise on electricity and magnetism. The telegraph equation by Heaviside, 1876. The discovery of the electron, 1897, decades after it was first predicted by Weber. Plum pudding model of the atom, J.J. Thomson, 1904. Finally, the gold foil experiment in 1911, and then the Bohr model of the atom, or the Rutherford Bohr model of the atom, 1913. A full 60 years after the initial model of the atom by Wilhelm Edvard Weber. And the telegraph equation, it's 1876 here. What did I have here? 1857, like almost 20 years earlier. It's truly and remember, Weber was predicting the discovery of the atom. Bohr, Rutherford and Bohr, when they came up with the model of the atom, it had already been proven that the atom existed along with a nucleus. So we're going to do a switch now, but I think it's important to have an idea of where all this came from. These British empiricists, they arose during the time in which fluid mechanics was starting to become a serious body. I mean, the work had been initiated in the 18th century with the mathematics of Euler and Lagrange, but it continued. But there's something interesting that took place, and we can sort of estimate of what happens by looking at the Encyclopedia Britannica. The Encyclopedia Britannica was sort of the internet of the day, or the Google search engine, or however you want to call it. And if you compare the 8th edition with the 9th edition, you see the massive increase in the number of copies, whether official or pirated, sold from 8,000 to 555,000. But what's interesting, if you go look at the scientific articles, the 8th edition, which was from the 1850s, when they were talking about fluids, they were talking about actual fluids. But when they moved on to the edition, they were talking about abstract fluids, perfect fluids. It's like, real science ultimately deals with actual things, actual atoms, actual fluids, but they're now moving on to abstraction. So there's something that's a bit tricky. Now, who wrote about electricity and magnetism in the Encyclopedia Britannica? It was James Clerk Maxwell. And who wrote about heat? William Thomson, later called Lord Kelvin. What this means is that the ability, how do you call it? The magnetophone, what's that in English? The megaphone. The megaphone available to people like James Clerk Maxwell and William Thomson to reach an educated audience was far greater than any scientific distribution network around people like Wilhelm Edward Weber. Now, what I would like to, I'm not going to focus, when I move on to the British empiricists, I'm not going to focus on the actual technical content of their ideas. What I want to focus on is the ideological presuppositions, which they make very clear in their own scientific articles, typically in the introductions, not always, but typically. And it's astonishing how clear they are saying, we're not doing things the old way. We've decided to do things the new way. So let's go back to our initial successful research program, the Luminiferous Ether. So the person in question is Gabriel Stokes. Now, what's interesting about Stokes, about William Thomson, about James Clerk Maxwell, they all studied at the University of Cambridge. They studied mathematics. They did not study physics. And furthermore, they all studied mathematics under the same tutor, a guy named Hopkins. So they all have a very similar background. Now, Stokes is known for writing the mathematics of fluid equations. The people talking about global warming and meteorology, they're always working with Napier-Stokes equations. Okay. So let's take an article that Stokes wrote in 1846 about the ether. He's considering work by Fresnel. So let's read Stokes. Fresnel supposes that the Earth passes through the ether without disturbing it, the ether penetrating the Earth quite freely. He supposes that a refracting medium moving with the Earth carries with it a quantity of ether. He supposes that light is propagated through this ether, of which part is moving with the Earth, and part is at rest in space. It may be observed, however, that the result would be the same if we suppose the whole of the ether within the Earth to move together, the ether entering the Earth in front and being immediately condensed and issuing from it behind, immediately rarefied, undergoing likewise sudden condensation or rarefaction in passing from one refracting medium to another. Okay, what's this guy saying? So Fresnel had an idea of the ether that was so fine that as the Earth moved, the ether didn't move. And all of the ether particles just sort of transparently went through the Earth. Given that the particles were so fine, essentially it didn't affect the Earth. Now, the Earth did have some effect on the ether, but broadly that is what it's saying. But Stokes is saying, no. Let's suppose that the ether is like strawberry jam, that the ether moves along with the Earth. And he's saying, it may be observed, however, that the result would be the same. Now, I haven't looked at the actual mathematics. It might be that the mathematics actually resembles each other. But I can certainly, just reading this, my idea is that they have nothing to do with each other. One is that the ether is like some sticky jelly or jam, and the other is that it's an incredibly fine ethereal entity. But the quote of his next paper is even more amazing. The phenomenon of aberration may be reconciled with the undulatory theory of light, as I have already shown. without making the violent supposition that the ether passes through the earth in its motion around the sun, but supposing, on the contrary, that the ether close to the surface of the earth is at rest relatively to the earth. Now, I don't know how the word, and this is not a mistranslation because George Gabriel Stokes was writing in English, and he was a graduate of Cambridge, of the University of Cambridge. So he was a highly educated native English speaker. I don't know how anyone can state that supposing that the ether passes freely through the earth is a violent supposition. Yet, this is what he wrote. So this is truly an ideological presupposition on the part of Stokes. Okay, so that gives us an idea of how the first project, what did I call it? The first successful research program was dealt with. Let's move on to the second. For that, we have to take a step backwards. So we go back to René Descartes. So Descartes' greatest achievement is to propose analytical geometry. Anyone who's used graph paper has ultimately used the Cartesian system of coordinates. Now, he didn't invent it. He was the first in the West to use it, because I've seen Chinese maps from around year 1000 where they're clearly using Cartesian coordinates long before Descartes was around, unless Descartes was able to travel back in time. Now, he declared that there was no void, so his corpuscles completely filled space, and that way, so the only way that there could be any motion was if everything was spinning around. So he developed this theory of vortices, and the vortices keep reappearing, as I wrote in one of my latest blog entries. So what did Descartes say? He said there's no real atoms the way we understand them. Or Lucretius in his De Re Naturam had written in the late Roman period. We also easily understand that it is not possible for any atoms or parts of matter, which are by their own nature indivisible, to exist. The reason is that if there were any such things, they would necessarily have to be extended. Extended means they occupy space, no matter how tiny they are imagined to be. We can, therefore, still conceive of each of them being divided into two or more smaller ones, and thus we know that they are divisible. This is simply an outright declaration on his part. There's no basis whatsoever. That line doesn't follow from the previous one. For it is impossible to clearly and distinctly conceive of dividing anything without knowing, from that very fact, that it is divisible. Because if we were to judge that same thing to be indivisible, our judgment would be in disagreement with our knowledge of it. Sorry, there's a typo. That should be our knowledge, not out knowledge. Anyway, Descartes is just talking complete nonsense here, but he's stating categorically there are no atoms, okay, in the way we understand them. So the next person of relevance is Roger Josip Bošković. In English, we often call him Roger Joseph Bošković. And he came up with, he was a Jesuit scholar of the early 18th century, and he wasn't talking about atoms. He was talking about points, which are simply centers of external forces, but they still have the property of inertia. So you have these mathematical entities which have the property of inertia. It's just like, yeah, right. So what he was essentially trying to do, and he writes this explicitly in his work, he was attempting to create some sort of intermediate between Newtonian bodies and like monads. Okay. So here's Bošković. That matter is unchangeable and consists of points that are perfectly simple, indivisible, and of no extent. In other words, they're infinitely small and separated from one another. That each of these points has a property of inertia. Remember, they're mathematical points, but they've got the property of inertia. and in addition, a mutual active force depending on the distance in such a way that if the distance is given, both the magnitude and the direction of this force are given, but if the distance is altered, so also is the force altered. Now, Bošković had a huge influence in the 19th century on Michael Faraday, on William Thomson, and even on others. I think, who is it? The Man and Superman. Who wrote that? The German philosopher Nietzsche. Nietzsche wrote about Bošković. So now we come back to the 19th century. Michael Faraday, the great experimenter, who discovered electromagnetic induction. He also started out in his scientific work. He discovered, as a chemist, so he discovered benzene. So he invented the lines of force. He didn't discover the lines of force, he invented them. He declared they exist. So let's read Michael Faraday. I am not ignorant that the mind is most powerfully drawn by the phenomena of crystallization, chemistry, and physics generally to the acknowledgement of centers of force. Centers of forces, that's the Bošković idea. I feel myself constrained for the present hypothetically to admit them and cannot do without them. But I feel great difficulty in the conception of atoms of matter. In other words, I don't like this idea of matter, which in solids, fluids, and vapors are supposed to be more or less apart from each other, with intervening space not occupied by atoms, and perceive great contradictions in the conclusions which flow from such a view. What is he saying here? He doesn't like action at a distance. Because if you've got intervening space between those atoms, even if they happen to be very close together, they would still be interacting at a distance without any intervening medium. He's saying he doesn't like the idea. How about William Thomson? Well, he was really interested in continental physics. You have to understand that continental physics, as understood by mathematicians in Britain in the middle of the 19th century, was essentially the revival of Cartesian physics. In other words, revival of Descartes' vortices. So he had vortices on the mind. He wrote a paper called Vortex Theory of Motion. He wrote several papers called Vortex Theory of Atoms. He referred explicitly to Bošković several times. He oversaw the first transatlantic telegraph cable construction, and for that was one of the reasons that he was knighted. But he also made many spectacularly wrong predictions. No balloon and no airplane will ever be practically successful. But he had an astonishing influence, both positive and negative, on the world of science. For example, when he declared categorically that there was no matter between the sun and the earth, that was in 1892. That was used as an excuse to simply throw out all of the observations made by Christian Birkeland, the Norwegian engineer and scientist, when he went to make all of his observations in Nordkapp in northern Norway of the aurora borealis, concluding that there was definitely electric currents between the sun and the earth. That was simply thrown out simply because William Thomson, later Baron Kelvin, had simply stated there's nothing between the earth and the sun. What did William Thomson say? After noticing Helmholtz, we'll see who is Helmholtz in a bit, Helmholtz's admirable discovery of the law of vortex motion in a perfect liquid. There's that perfect liquid, that ideal liquid, ideal fluid, that is in a fluid perfectly destitute of viscosity or fluid friction. The author said that this discovery inevitably suggests the idea that Helmholtz's rings are the only true atoms. Now, this is in 1868. He's written that already in 1852, Wilhelm Edward Weber had already posited that there was an atom with negative charges going around positive charges. This is 16 years later. For the only pretext seeming to justify the monstrous assumption of infinitely strong and infinitely rigid pieces of matter. It's like Stokes with his violent, talking about the violent supposition of Fresnel. the existence of which is asserted as a probable hypothesis by some of the greatest modern chemists in their rashly worded introductory statements, is that urged by Lucretius and adopted by Newton, that it seems necessary to account for the unalterable distinguishing qualities of different kinds of matter. So it's interesting that it is the British who threw Newton under the bus. James Clerk Maxwell follows. He mathematized Faraday's lines of force into the magnetic and electric fields. And with Boltzman, he wrote about the kinetic theory of gases. Well, what does Clerk Maxwell write? These German physical hypotheses, however, are entirely alien from the way of looking at things which I adopt. In other words, I'm going to throw away everything that works, and I'm just going to come up with my own explanations. And one object which I have in view is that some of those who wish to study electricity may, by reading this treatise, that's his treatise on electricity and magnetism, come to see that there is another way of treating the subject, which is no less fitted to explain the phenomena, and which, though in some parts it may appear less definite. In other words, I don't know. In other words, there's some stuff which that gives nowhere near the same accuracy of predictions as what was previously defined by Weber, corresponds, as I think, more faithfully with our actual knowledge, both in what it affirms and in what it leaves undecided. Okay, so now we move to the Allies in Germany, Hermann von Helmholtz. That's important. He didn't study as a physicist. He studied as a physician. He was a real Anglophile. In other words, he loved the British. He, after his 1847 paper about the conservation of force, he was invited over to Britain for several weeks. He was feted everywhere he went. He was treated regally for weeks, and he translated into German the treatise on natural philosophy written by Thomson and Tate. What does he? So in a response to scathing critique of the translation that he had made of Thomson and Tate, done by Zöllner, Hermann von Helmholtz published something in Nature, the British journal. Among the scientific investigators who've especially directed their efforts towards the purification of physical science from all metaphysical infection and from all arbitrary hypotheses, and on the contrary, has striven to make it more and more a simple and faithful expression of the laws of the facts, Sir William Thomson occupies one of the first places, and he has consciously made precisely this his aim from the beginning of his scientific career. I think I've already given you an idea that this purification of physical science from all metaphysical infection was simply infesting physical science with more metaphysics for from purely arbitrary perspective. I think that's the message that I'm trying to state. And here we see that William Thomson and Hermann von Helmholtz together were a pretty petty pair. In 1881, it was time to start choosing the international set of units for the various things that had been discovered. Now, who actually came up with the idea of having such units? Two unknown Germans named Karl Gauss and Wilhelm Edward Weber. But the meeting took place in 1881, and who was the German representative? Hermann von Helmholtz. And who was the British representative? William Thomson. And so here they come, and there's a plenary meeting to discuss these things. And here's the secretary, Eleuthère Mascar. As we still only had two units, the ohm and the volt, and it was necessary to complete the system, I asked the president, Monsieur Courchéry, if the commissions could at least meet. I had to bow to his negative response, and we stayed with von Helmholtz near Lord and Lady Kelvin, who, having neglected to eat lunch, were having a chocolat in the Chibou restaurant located near the Congress Hall. It was in this small committee, around a common white marble table, that the following three units were agreed. Ampere instead of Weber for electric current, Coulomb and Faraday in honor of Faraday. Now, the point was that both in Britain and in Germany, people were already using the term Weber to describe the element. So the point is that Thomson and Helmholtz conspired openly to get rid of any reference to Weber for the set of units. Now, later, once Weber had passed away, Thomson had passed away, Weber was given a unit. It was given for the magnetic flux, but the magnetic flux presupposes the magnetic field, and never would Wilhelm Edward Weber have ever referred to a magnetic flux. The irony. And then we move on to Ludwig Edward Boltzmann, who with Clerk Maxwell developed the kinetic theory of gases. We're told he defined entropy, and it's interesting, he opposed the atomic theory. Hold on, is that true? I'm sorry, that last line might have been a mistake on my part. It might be mixing it up with someone else. No, I think he supported the atomic theory. I think it was, yeah, Ernst Mach opposed the atomic theory. Okay, but we're not talking about Ernst Mach today. Anyway, it's not relevant to so scratch that last line. So Boltzmann is writing in 1899, so this is 18 years after the death of Weber, about the fact that Weber's theory of electrodynamics has been replaced. Let's read the language he's using. The first attack on the scientific system described was directed against its weakest side, Weber's theory of electrodynamics. This is, so to speak, the flower of the intellectual work of that gifted inquirer who has earned the most immortal merit on behalf of electric theory by his many ideas and experimental results recorded in the system of electrodynamic units and elsewhere. Let's stop at this one. So he's saying that, look, Weber was an absolutely brilliant guy. Okay. And then we go on to this sort of the same kind of language used by Stokes, William Thomson. However, for all its ingenuity and mathematical subtlety, it bears so much the stamp of artificiality, whatever that means. As all human endeavor is artificial by definition, all right? It's human invented. That there can surely never have been more than a few enthusiastic followers who believed unconditionally in its correctness. In other words, all these people are crazy to have believed that Weber's work, despite the fact that there was huge experimental evidence as well as brilliant theoretical work, was simply to be thrown out. It was Maxwell who attacked it while giving fullest recognition to Weber's achievements. You see, Maxwell was fully honest. That's what he's saying. And so the fact that Maxwell came up with a different, we should all believe Maxwell. Just trust me, because Weber's work was artificial. But here's from the same text. This is a sort of memoir. So Weber's electrodynamic theory fared similarly. It is based, as we have seen, on the assumption that the effect of electric masses depends on their relative motion. And just when its inadequacy was definitely proved, Roland found by a direct experiment in Helmholtz's laboratory that moving charges act differently from stationary ones. Well, no. Its inadequacy was not definitely proved. Its adequacy was definitely proved by Roland's experiment. In earlier periods, one might have felt inclined to regard this as a direct proof that Weber's theory was correct. Well, that's correct. It is direct proof that Weber's theory is correct because it was predicted. Today we know that it is not a crucial experiment, but it follows also from Maxwell's theory. Yeah, but Maxwell's theory was tweaked to take into account this result. All right. Sorry, I'm getting too excited. Now, not everyone was happy with the situation, so let's look at some aspects of resistance. First, André-Marie Ampere himself in 1823. This is after the discoveries by Ørsted. And Ampere recognized instantly that the people who were talking about what would be called later the magnetic field were reviving Cartesian physics, were reviving the vortices. So here let's read. By seeing the planets revolving around the sun, Cartesian physics imagines that they are pushed in the sense in which they move by vortices revolving in the same sense. When it, i.e. Cartesian physics, pole of a magnet carried to the right and the other pole carried to the left of a conducting wire, it supposes a vortex independent of the wire. Newtonian physics explains all celestial phenomena by an attraction directed along the straight line connecting the two interacting particles, and the motion is a complicated result of this attraction. As regards the new electromagnetic and electrodynamic phenomena, I make what Newton has done for celestial motions, namely, I explain them by attractive and repulsive forces. That was Ampere, already in 1823. He's calling them out. So he criticized Faraday explicitly for violating Newton's third law. Almost a century later, Jules-Henri Poincaré was a brilliant mathematician. There's mathematics with so many different results and principles and so on and so forth associated with Poincaré. He was the first one to write about relativity. Many people say that Einstein plagiarized Poincaré, but didn't quite get the math right. But that's a different story. That's another talk or another set of talks. Okay. Well, what did Poincaré write about Maxwell? For a mind accustomed to admiring the models of people like Laplace or Cauchy, a theory is not easily satisfactory. In other words, to satisfy people who are used to reading wonderful models, you need to do serious work. It's hard. Not only will he not tolerate the slightest appearance of contradiction, but he will demand that the various parts be logically linked together and that the number of hypotheses be reduced to a minimum. This is very different from the language that the British and their German allies are using. Right? It's the whole thing has to fit together. The English scientist, this is Clerk Maxwell, does not seek to build a single definitive and well-ordered edifice. Rather, he seems to be erecting a large number of provisional and independent constructions between which communication is difficult and sometimes impossible. In other words, the different aspects of physics have now been separated into different components, and you can't, and there is no possibility of creating a well-ordered whole. Now, Poincaré was pulling his punches. He was being polite. But his colleague, Pierre Duhem, who was both a theoretical physicist and historian of science, and who wrote extensively on medieval and pre-Galilean science, he had different words from James Clerk Maxwell. Let's read him. At every moment between the best established and most universally accepted laws of electricity and magnetism and the equations imposed by algebraic analogy or mechanical interpretation, the disagreement bursts forth. At every moment, it seems that the very sequence of his reasoning and calculations will lead Maxwell to an impossibility, to a contradiction. But just as the contradiction is about to become clear, just as the impossibility is about to become obvious, Maxwell makes a troublesome term disappear, changes an unacceptable sign, i.e. plus to minus or minus to plus, transforms the meaning of a letter. Then, having taken the dangerous step, the new electrical theory, enriched by a paralogism, continues its deductions. I mean, this is scathing. This is truly scathing criticism. Essentially saying that James Clerk Maxwell is a fraud. I was truly astonished when I came across this quotation. These are serious words. Let's move to today's world. So the late Peter Grano, who was professor at MIT, and his son, Neil Grano, I'm not sure what exact his position was, but he worked at the University of Oxford. Each was a brilliant researcher. They also had a long-standing collaboration, father and son pair. And they conducted many, many experiments in support of Ampere. But they're also extreme supporters of Ernst Mach and extreme and they hold the most extreme vision of the action at a distance idea. For them, all matter instantaneously senses all other matter in the universe. It was already demonstrated by Pierre-Simon Laplace in the 18th century that for gravity to work and the solar system to remain stable, gravity has to be moving at least 10 billion times as fast as the speed of light. This was similar calculations were done by Tom van Flandern in the late 20th century, and it's unimaginable speeds are necessary for gravity to work. In other words, there is no speed limit of 3 times 10 to the 8 meters per second that we're told comes from relativity from Einstein. All right. Anyway, so the Peter Granot and Neil Granot, they were clearly pushing in support of Ampere, and also in terms of also Ernst Mach. One of the Granots, I think it was Peter Granot, he was co-author. Oh, sorry. There's a quote from Neil Granot about the field theory. Maxwell in the 1870s was on a self-proclaimed mission to develop a field theory specifically to introduce an undetectable substance that inhabited the space between all pieces of matter with as many properties as required to explain all known experiments. That's similar to Duhem and this idea that, yeah, we're just going to invent all the properties needed to correspond to whatever we see in the experiments. So this sounds very much like Bošković. For no reason other than fashion, this new field theory approach became popular in England and within 20 years had pervaded continental Europe, and the rest of the scientific world, and the instantaneous action at the distance era came to an end. Who's next? André Assis. He co-wrote papers with Peter Granot, and I think Neil Granot as well. He has spent his life reviving the work of Weber. But not just Weber. He organized a translation of Coulomb, of Ampere, and Weber into English. He revived Weberian electrodynamics. He revived Mach's principle, like the Granots. And he invented his own relational mechanics, which takes all of this together, which is worthy of another talk on many blog posts and so on and so forth to come. So here's some books that have been published by André Assis, the translations of Coulomb, Ampere, 4 volumes of Weber. There's a 5th one coming out. He's also written explicitly himself about Weber's electrodynamics. Unfortunately, the left book is incredibly expensive, and the next one I can't find on the internet, not even as a used copy. Sylvie. And finally, but not by no means, I came across this PhD thesis published in September 2022 at the University of Liverpool. The aspects of Weber electrodynamics. The external examiner was Neil Granot himself, and this is Christoph Baumgärtel. And reading it, there's many interesting leads, including talking about the relationship between plasma physics and Weberian electrodynamics and so on and so forth. The point is, the resistance is there, it's growing. Has it taken over all of science? No, of course not, by no means. However, there clearly are people who keep coming back to the ideas and say they're worth looking at, they're worth looking at, they're worth looking at. So it's time for some kind of conclusion. With 60 slides, I took just over 1 hour. That's okay. So, first, there's renewal of interest in the work of André-Marie Ampère and Wilhelm Edward Weber. Newton's third law is crucial. And already in 1822, Ampère wrote to Faraday directly, stating that his lines of force were violating the law. Now, Caluzzi and Assis, they disproved in 1996 Helmholtz's claim that Weber's law did not conserve energy. This is crucial because that claim that Weber's law did not conserve energy is how Helmholtz and Thomson kept attacking Weber. It was a spurious accusation. It was wrong. So the question comes back to the very beginning of the talk, where I talked about these two successful research programs, one talking about the properties of light and the other talking about the properties of electricity. What is the relationship between the two? Then, of course, it's now understood that most of the universe's matter is in the form of plasma. So what would plasma physics look like from a Weberian perspective? When you're talking about plasma, you're always talking about Birkeland currents. And Birkeland currents are these two twisted pairs that are crushed together by the magnetic field. But if you don't have a magnetic field, but you still have the crushing together of the two currents, then the twisted pairs, then what exactly is taking place inside a Birkeland current? Next question, is there a simple explanation for quantum mechanics? Well, one of my subscribers, his name is Hans Schantz, and he's writing a book right now about electrodynamics and the relationship with quantum mechanics, and he claims that quantum mechanics can be understood deterministically using pilot waves, the pilot waves proposed by de Broglie. So that. It may well be that all of this stuff can hold together, but someone has to do the work, or many people have to do the work. But I have another interesting thing. I came across something else from the glory days of the early École Polytechnique. It turns out that heat death was promoted by all of the people participating in the anti-Weber movement. William Thomson, Hermann von Helmholtz, Clausius, Boltzman. So I have a question. Did the work of Lazare and Sadi Carnot, another father and son pair, on thermodynamics suffer the same treatment as did the work of Fresnel and Ampere? Because Sadi Carnot was accused by no less than William Thomson of having violated the principle of conservation of energy. Oh, that sounds familiar. That's exactly what they accused Weber of having done. So my conclusion for today is there are so many contradictions in theoretical physics today that we need to recheck and redo absolutely everything since the glory days of the early École Polytechnique. Everything needs to be rethought, restudied, re-understood, reconfirmed. New experiments need to be done to distinguish the subtleties between different theories, and so on and so on and so forth. So thank you for listening. I hope you enjoyed it.
Yeah, thank you, John. Yeah, that's comprehensive, and glad that we got that recorded as a reference piece to refer back to. A lot of good questions. I got a couple of questions that popped into my mind, actually touching on the ether, and so did Jerry. So I'll defer to Jerry, and I'll see if we have similar questions or if they're different. But Jerry, you can go first.
All right, thanks, Matt, and thanks, John. That was a wonderful presentation. I enjoyed it. I have about 50 years worth of questions for you, but I'll just limit it to one. When I was a young lad and I went to college and I studied electricity and electronics, I came to the conclusion that they couldn't explain why it worked. They could tell you how, and we could measure it and do all kinds of things with it, but none of the theories explained it, and I was very confused. So I read a lot of stuff. I read Maxwell. I remember reading Poincaré and Lorentz and a lot of this stuff. And then I read this, I think it was Scientific American, and it was all about the idea of the solar wind. And I think it was a book by a Russian. I don't remember. This was 50 years ago. And I was so intrigued by this concept of the solar wind that in my mind, I said, that is the ether. You know, you have the sun and just this almost infinite number of charged particles coming out of it constantly. And you have all these billions and trillions of suns in the universe. The whole universe is completely filled with this solar wind. But anyway, whenever anyone says ether, in my mind, all I can think of is a solar wind. And I just wanted to get your thoughts on that, if I can, John.
Well, what's called the solar wind is positive ions and electrons moving. Okay, so this is corporeal matter. So this isn't the ether. The ether is much fine. If the ether exists, the ether is much finer particles, which flow through these larger charged particles. The solar wind is simply a way of saying electric current without talking about electric currents in space. This is one of the problems with astrophysics. Is they keep coming up with terms so that they can avoid saying that there are electric currents in space. Now, the solar wind is really some kind of diffuse electric current, and of course we're told that the plasmas are neutral overall. They aren't, but and that they're initially it was understood that they had infinite resistivity, and then they went to zero resistivity after Alfvén published a paper in 1942, and when Alfvén received his Nobel Prize in 1970, he said, "Look, you guys got it all wrong. You didn't. I was giving you a simplification, and it was a bad idea because you all took the simplification and accepted it as reality." So I'm sorry to have done that, but thank you for the Nobel Prize anyway. I think the crucial thing about the so-called solar wind is that there is huge amounts of electrical activity between the celestial bodies. I think that's the most important thing to retain. Now, the ether is about trying to give an explanation for why light exists, and also explaining the properties of light. Fresnel was able to explain diffraction. He was able to explain polarization of light, and so this has been once Maxwell came up with his fields, the ether was replaced with some sort of field that had all of the properties, because he kept adding properties to the field until it sort of works. But as we saw with Duham's criticism, it's pretty vicious. I myself don't know. I mean, I think there is an ether. I suspect that Weber was correct. There is an ether, and the ether is charged particles, but they're of a much finer granularity, so the charges will be much smaller than the charges of the things like electrons and protons and so on and so forth. But whether the electrons and protons themselves have structure and inside are actually miniature universes, or themselves with their own. I mean, it sounds intriguing, but as far as we know, protons and electrons are pretty stable. So I don't know if I've answered anything that you want, or whether I've satisfied you anything, but.
No, that's good. It's given me more food for thought.
Well, we can discuss this later. Yeah.
I guess, yeah, my question on the ether might be a bit more basic. So in just going through some of this history, and some of the different conflicting ideas of what the ether might be, is it empty space? If it is an ether, what type of ether would it be? You've illustrated a couple of ideas, but in your research, would you be able to outline like what would be the dominant different ideas of the ether? Because I noticed like looking at a lot of these British scientists of the 19th century, a lot of them they've got conflicts. You know, some are trying to like talk to ghosts and mediums, and they have these posits of the spiritualist that's where ghosts and demons can be communicated with through the ether, and then other people have a different view. So and then like is it a bunch of particles, or is it so? is it a fixed thing ultimately, or is it a fluid thing? So what would you be able to say, like, what would be the dominant quick definitions of the basic models, or is there too many to think about?
Not really. But the point is that the exact nature, so during the 19th century, there's huge efforts being put in by a number of researchers to try to come up with various kinds of mechanical models of an ether. So they were essentially working with some notion of a fluid, but what was the elasticity of this fluid? What was the viscosity of this fluid? As we saw with the Stokes versus Fresnel, when a body moves through the ether, does the ether flow naturally through the body, or does the body drag along a large quantity of ether inside it? And what was interesting from the words of Stokes was the idea that the ether has to continually transform itself as the ether has to continually transform itself as it enters and leaves the body. And so it seems to me that if you like to use Occam's razor, Stokes's approach to the ether in the body is very much a violation of Occam's razor, because this is the ether is continually changing as it enters the body and as it leaves the body. For me, that doesn't sound like an ether the way Fresnel or Huygens imagined it. For them, it was some incredibly fine particles that were so small that they were essentially untouched, or for the most part, untouched by corporeal matter. And they permeate the ball. They permeate all the free space between the but the exact details, ultimately, these came about as different experiments were done, Friso and then the Michelson-Morley experiments and so on and so forth. I don't know enough. Honestly, I must say, for the moment, I don't yet know enough to be able to really competently talk about them. But that could come later. That could come later. But initially for this talk, I was trying to show that the reasons that they were attacking the work of people like Fresnel or Ampere or Weber had nothing to do with technical reasons, had nothing to do with scientific experiments. It was for ideological reasons. Now, what follows in your discussion about people who believed in mediums and weird spirituality and occult forces and this and that and the other thing, I think that was perhaps a natural consequence of the approach taken by the British empiricists in replacing the continental science.
Yeah, I suspect so. All right. I'll withhold my follow-up question for the moment. There's a couple of people who popped their names on. Let me just scroll up a little bit here. The first question I saw was from Richard. Richard, do you want to ask a specific question, or do you just want me to read your question to John? I'll just read the question. Richard is asking, do you know about the electric universe thunderbolts movement more generally? And
Thunderbolts info. Okay, so I first heard about the electric universe when I lived in Australia. So I immediately contacted the lead scientist at the time, the late Wal Thornhill, who passed away approximately a year ago. And I consider, even though I didn't meet him very many times, I considered him to be a great friend. And when I started out my blog, I wanted to contact him, and unfortunately I found out, unfortunately, he has left us. Wall was a brilliant individual, and I think the electric universe isn't a single theory. It's more of a collection of theories that all presuppose the idea that electricity is the dominant force in the universe. So it has multiple adherents, but the adherents wouldn't necessarily agree on all details. But I think the general precept that electricity is the primary force in the universe is correct. We do not live in a gravitic universe. We live in an electric universe. And I think that is why it is so important to restudy these debates of the 19th century, which, as I have tried to say with respect to the reintroduction of Descartes' vortices, are in fact a rehabilitation of or the resurfacing of 17th century debates. I think it's crucial to try to understand what electricity really is. So the previous question from Gerald, what is electricity? I don't really know what it is. I can write down the equations, I can manipulate things, I can describe things. Sure. But what really is electricity? I don't think we all know. I don't think any of us really knows. Let's see. And I remember asking Wall once what he thought of the work of André Assis, and he thought André Assis deserved the Nobel Prize because of he spent so much work reviving Weber.
Well,
Would you like to add more, Richard?
yeah, Richard, you still there?
Well, no, thank you for that. I mean, I've been following the electric universe for a long time, and they've got so many things happening in the universe that they clearly explain, so it's worth looking at for anyone. There's another model. It's called the structured atom model. Kale. I don't know if you know about that.
I've read his book.
Okay.
I find it fascinating. The question, the Rising Tide Foundation hosted André Assis discussing, and André Assis was talking about this 10 to the minus 15 meters associated with the at which point the repulsion of the positive charges towards each other becomes an attraction. But that only happens if they're moving with each other, with respect to each other. So they're not in a static configuration. And so the question while the SAM model sort of assumes that everything is static inside the everything is static inside the nucleus. So there you have, it's a little bit like the ether versus action at distance questions. Here you have two models that, at least on the surface, do not appear to be compatible. And so it would be interesting. I think it requires a lot more serious thought. But I am fundamentally in agreement with the idea that the nucleus must have structure. The question is, what exactly is its structure?
Yeah.
And clearly, electric forces must play a key role. And there's no such thing as a magic strong force holding everything together. So in that sense, on those general principles, I would fully agree with the SAM model. But whether it can be explained fully by electrostatics, I don't know. But I do find intriguing the idea that the neutron is simply an electron-proton pair.
Yeah. Well,
that within 17 minutes, once it's taken out of a nucleus, it just naturally disintegrates into two components. But that still doesn't explain to us why one has a mass that's 1,800 times bigger than the other.
It strikes me, looking at the SAM model, that it smells similar to the sort of thing that emerged with Kepler in the Mysterium Cosmographicum, like his first youthful attempt at finding a potent theory for the reasons why the configuration, why things move and why they are the way they are instead of some other way, some other imaginable configuration. And so he had this potent idea that he outlines regarding the nesting of the solids in a certain lawful way to generate certain proportions. But then it has a rigidity that we don't find in nature. He had to ultimately let go of it because it got close to having a lot of descriptions, but it was too wrong to be used beyond a certain point, though he still thought it was high value in putting him on a very potent pathway of discoveries. And it feels like, I don't know if you agree with this or not, it feels like, looking at the SAM model, something similar is a very potent set of hypotheses utilizing.
Well, I think am I on?
Yeah.
Yeah. So I think there's more to it than that. I think it's more because if we look at the SAM model, it talks about the subtleties of the properties of various isotopes, how with exactly the same number of protons and what are they called?
Electrons?
Internal electrons, was that the term that's used in the SAM model?
Oh, internucleic electrons or internucleic
Yes,
protons.
and so they is that
Electrons.
you get the movement of one of the protons to some other part of the nucleus, and you get a completely different isotope. You get a different isotope of a different element, and one is stable and the other isn't, and this would be compatible with certain notions of low temperature fusion, and would also explain why certain why fission occurs with certain kinds of isotopes, but not with others. And if you look at the internal geometry as proposed in the third chapter of the book, then you get an idea of where the thing becomes unstable. So I think it's more than just the level of the Mysterium Cosmographicum, which is just talking with about, what is it, 6 solids. There's a lot more there's a lot of
Oh,
isotopes.
five solids. Yeah.
5 solids, okay. But still, it assumes that it's static inside, at least the way it's described in the book, but that doesn't seem to be compatible with Weber's description. So this is why I have, especially given I'm neither a professional chemist nor a professional physicist, I'm hesitant to make any concrete statements about this. But still, I think both ideas are very interesting. The question is whether they're compatible or whether they're mutually contradictory. I don't know.
Well, could you say again the Weber statement on that particular thing?
So Weber's fourth law, when the charges are the same, normally things are repelled. But when they come within a certain distance, a key distance within each other, the mutual repulsion becomes a mutual attraction. And so the idea is that they would hold, these positive charges would hold the nucleus together. And that's the force law that I presented in the slide is exactly the force law that we're talking about. It's not that there's no hack involved. There's no, and that comes from the negative sign that appears in the, in front of the part pertaining to relative velocity.
Well, it's like he's adding an assumption then. So like with the SAM model, you know that electrons attract protons, and you're just using that only. Sure. Whereas he is making this property of protons up. So it seems
no,
SAM model is simpler.
No, because his model is a model of electricity that happens to produce a model of the atom.
Okay.
The model of the atom is not some ad hoc supposition on top. It follows from his electric force law. So that's really the amazing thing about it, because writing about electricity ends up predicting atoms long before anyone could demonstrate that there were atoms. I mean, the people like Ernst Mach, their entire lives believed that atoms didn't exist. And as we saw, Faraday didn't like atoms. William Thomson didn't like atoms. They had something against matter. In that sense, that answers a bit the question from Matt about these people who believed in weird spiritual forces that have nothing to do with reality. Because they literally didn't, a lot of these British empiricists, for some reason, they hated the idea of real matter. I don't know. I don't know why. I mean, what's his name? William Thompson had a beautiful yacht that probably needed 40 people to man.
That's pretty funny.
Longitudinal
Hold on.
electromagnetic waves.
I think they're I asked this from André Assis, and he says that they follow naturally from Ampere's work. That they're not. They're on the other hand, Heaviside thought that this was impossible. So that's another step in favor of the Ampere Weber approach.
So,
Richard,
Richard, I'm so sorry, Richard. I'm so sorry. We just got a lot of people who are waiting in line to to pose a question. But if we have time, we'll circle back. Kelly, I know you've been waiting.
Thank you, Richard.
Yeah, thanks, Richard.
Hi, John. Yeah, I'd just like to thank you for your presentation. You did a pretty good timeline. Like, I've studied this myself in the past and trying to, like, I always knew something was up too, and how our authorities, we made these decisions, and I always thought something was up, and you did a pretty good job trying to explain things. So I'm writing frantically. Like, a lot of things I have were just my personal questions, but one of the people you mentioned near the end, the father and son, Neil Grenot and his father Peter.
Yes.
And they mentioned something about the idea of, like, all matter, whenever there's an action in the universe, they said it instantly reacts to every other place in the universe. And it sounds like a cool concept. I don't know if we can ever really prove that. But I'd like to know where they're coming from. It leads me to stuff that I've always thought of. I don't know.
They wrote a book called Newtonian Electrodynamics together, which is focusing on Ampere. They also wrote a book together on inertia, and so inertia. I guess the concept of inertia was first discovered under limited circumstances by Galileo. The word inertia comes from Kepler, but he wasn't using it in exactly the same ideas. It became clearly stated in the modern sense by Newton, and but the problem with Newton is that inertia was defined when he was talking about motion of bodies and stuff. The question is always, with respect to what? So Newton refers to absolute space. Now Leibniz legitimately criticized Newton. What the hell does absolute space mean? Can you touch absolute space? Can you measure absolute space? Can you do anything with absolute space? What does it mean? If everything's moving, how can you talk about absolute space? How can you refer to it? All right. Now, Ernst Mach picked up on this idea in the 19th century. He said, well, actually, it's not with respect to absolute space. It was respect to the rest of the matter in the universe. So
Mach, he was the guy. He had something to do with relative motion.
No, Mach was saying that. So I remember the picture of André Assis, he's holding a bucket. So that's Newton's bucket for the Newton's bucket experiment. So you take the thing and you spin it around, and the water moves up. Actually, he's always using Brazilian coffee because it's black, so it's easier to see. But the same idea. So the water rushes up on the sides of the bucket or the container in which it's doing. So why is it doing that? It's because it's being attracted to the rest of the matter in the universe.
Right.
So the Granols have taken up this idea to the extreme and said that, in fact, it's all of the matter of the universe, not just the matter that's not too far from us. and it's instantaneous.
Yeah, I was kind of thinking in terms of,
So they wrote a book called Newton versus Einstein, or Newton and Einstein. I ordered the book about 3 months ago. Unfortunately, mail to Colombia is problematically slow, and I was told that it reached customs in Bogota on January 24th. It still hasn't arrived in my home, despite the fact that I live in Bogota.
so we'll know more later.
That's right. Yeah. But I
Yeah,
think
like
all these discussions that people, what do you think about this? What do you think about what's it? I think they're all interrelated. All of these questions,
Yeah.
I think, are all interrelated. I don't think it's, oh, we'll solve this and then we'll go back and solve this. No, I think that answering one helps answer the others. I think the answers are all interrelated. They're not the same answer, but they're interrelated.
yeah, like right now we're
Ellie, I'm so sorry, man.
okay. I'm sorry.
Yeah, we just have a limited amount of time, but we have a lot of people waiting for questions. So sorry. I know it's a very engaging topic, and we can have a whole philosophical conversation, right, about any
Oh
element.
yeah.
So it's difficult. But Roger, you still there?
Thanks, John. I really enjoyed your erudition on the history of the development of physics. But one thing that they've solved and been able to correctly define in the terms of what is the stuff of it is what is energy. Their best idea is to define it as the capacity for doing work. That's not very, very helpful. Do you have any idea? Seriously?
No,
stupid.
I think this question may well be the kind of stuff that would be the content if there was a follow-on lecture on whether the same treatment was applied to Carnot and his father as was applied to Fresnel and to there's some really weird stuff. It's like Joule. He had some idea about thermodynamics, which was completely incompatible with Carnot's approach to thermodynamics. But Joule's stuff didn't seem, from what I understand, didn't seem to make sense. But somehow there was some magic trick that was done so that Joule's work and Carnot's work was combined into some new model. And then heat death appeared in 1852. Who was the first one to propose heat death? Oh, William Thomson was the first one to talk about heat death in 1852.
We'll need to speak up, mate.
13 years before Boltzman wrote about entropy. So it's not that heat death follows from entropy, it's that entropy follows from heat death.
We think your hand is in the way of your mic.
I'm sorry.
Oh, that's better.
I'm sorry.
It's the full force of your brilliance.
So did you hear what I said? Do I need to repeat it?
I didn't get much of it.
Okay, so what I was saying is that the heat death first appeared or was first proposed by William Thomson, I believe in 1852.
Yeah.
And that was 13 years before Boltzmann wrote about entropy. So when we're told that entropy leads to heat death, or the entropy only increasing leading to heat death, that's sort of like a post facto explanation. They'd already come up with the concept of heat death. All right, so I honestly, I don't know enough about this stuff, but I just find it crazy that James Joule had talked, so he had his own notion of thermodynamics and energy and so on and so forth, and it wasn't compatible with, and it seemed to be contradictory, and it wasn't compatible with Carnot's, and then there were some magic tricks that were applied, and they finally came up with a model that sort of combined the two. And so it seems to me that there's some pretty suspect stuff that has been done, but I don't know the details.
Yeah,
I think your comment is appropriate.
Yeah, among physicists, it's a lost cause trying to get them to state or define or elucidate what is the stuff of this material that they say is there, that they measure and all the rest of it. I run a research team that are involved mainly in the realm of human spirituality. I don't use the word consciousness because even the pundits that tout that word and subject can't define it, have not defined it. But our observation is that the primordial energy in the universe is our spiritual life force, which when directed gives us that which we observe, which, you know, and you can block it and cause ridges and all sorts of things. So particular locations of ridges and such can be produced if you want to. People do it when they argue with each other. They get very solid clump. Yeah,
I don't know. I really don't
it's
know.
a big subject. It's that, you know, carrying out experiments to prove it. Hard work, mate.
Oh yeah. It's all hard work, everything, because first of all, coming up with crazy ideas is hard work. But then once you have the crazy idea, then trying to validate it, trying to imagine what kind of experiments can be done to validate this idea.
Right.
And then, okay, you start to have some experiments that seem to be going in the correct direction. How do you quantify these questions to make it even more so that they can later be useful, perhaps to develop technology or perhaps to better understand processes? It always requires hard work. So even if you have the correct idea, the correct intuition, from there to actual validating it might take decades.
Yeah,
It's hard
making it
work,
real tough.
and not just by a single person working. It could be many people working.
Yeah.
Thank you.
You're welcome. Well, thank you for your work. It's very much appreciated. And in my humble opinion, as an 88-year-old guy that's dealt with this forever in 5 days, you were quite brilliant.
Thank you. Thank you. Thank you.
All right, we've got a couple more questions. Monty just recommends that people check out Plato, read some of his dialogues also to help develop an edge in cutting through this. I concur. Yeah, good. Specie is asking a bunch of questions. I would just ask Specie that maybe you condense it to a select 1 or 2 questions, but go for it if you're still there. Are you still there, Specie person? Okay, I guess
Species still here, but it's
yeah,
just
there's
not
an issue with
unmuted.
the microphone, I guess. So I'll just read one, I guess, that caught my eye. Benjamin Franklin's research into electrostatics assumption of, is this an assumption, or did he have an assumption of the existence of the ether? That's
I unfortunately know nothing about the work of Benjamin Franklin. I hate to mention it in front of you, Matt, but
that's fine. It's all good. Yeah.
I do see some stuff about the Earther, for example, the element proposed by Dmitry Mendeleev. I've heard of this. I don't know the details. Personally, I believe there is some kind of ether, but what its properties are, what it might be made of, I honestly don't know. I like to imagine that the universe is self-similar at different scales. So what would that mean? So if we had our ether microscope, whatever that might look like, we might find that at the ether level, you also have filamentary structures between microether particles that would look like the filamentary structures that we are seeing with the James Webb telescope, or that we see inside brain images. But that's just a pure speculation on my part. I have no confirmation or no way of verifying any of this.
Cool.
I hope that answers something.
At the very least, just being able to define questions has more value sometimes than getting closed answers. So that does the job. Yeah, I think we've been through quite a bit here. There was another question Specie had on Tesla. I guess I'll just read it. Serbian-American author or electrical engineer Tesla wrote, quote, long ago, mankind recognized that all perceptible matter comes from a primary substance of a tenuity beyond conception, filling all space, the akasa, or the luminiferous ether, which is acted upon by the life-giving prana, or creative force, calling into existence in never-ending cycles, all things and phenomena. Thank you.
Tesla did talk about vortices. So in that sense, I suspect he was channeling at least some aspects of Descartes. But I haven't got around to studying Tesla in detail. So I cannot go beyond talking about generalities and the kind of pop stuff that everyone knows, or at least they think they know about Tesla. That's all I can say for the moment. I mean, I started this study of 19th century science a few months ago, expecting to find, or thinking that there might be some conscious action on the part of the British empiricists to replace continental science. I didn't realize how easy it would be to find the smoking guns. I was astonished at how openly they wrote about what they were doing.
Yeah.
They didn't hide at all what they were doing. It was not some secret, we're going to do everything in the dark sort of thing. No. I mean, they may well have had private meeting, and of course, then they would have had private meetings and discussed certain things about what they intended to do. But they wrote openly about what they intended to do and what they were doing. It was not hidden. What's the expression? Hidden in plain sight.
Yeah, I got another interesting point to look at for people who might be doing this research, just throwing it out there, is I don't know if you've heard of Stephen Gray or James Flamsteed.
So they were early workers on electricity at the time of Newton, and Newton wasn't exactly despite the fact that he was a brilliant character, he was not a nice person, and he certainly did not help out the careers of Flamsteed or Gray. That's for sure. André Assis has written a little bit about.
Oh yes.
Gray.
Yeah, in looking at
a few paragraphs here and there.
Oh, that's so interesting. Because yeah, I'm getting the sense looking at Gray and his work on on electricity, that this is what inspired Ben Franklin to carry those experiments to another level around that same time when he was in England. And this book called Newton's Tyranny is a short little book written by a father-son team, and it's a really interesting book, just going through the work of Coates and a bunch of these characters around Newton to systematically just destroy Flamsteed, the astronomer, and Gray, and annihilate them. But really interesting work has been done on this stuff. So, but I've never seen anybody link it to Ben Franklin, though I feel like that connection is there. They're doing the same experiments and stuff. So again, there's a lot of discoveries to be remade, I think, in this very potent field of exploration. So it's really nice that you've demonstrated how this can be done, just journeying in this realm that people are often taught, oh, you can't you can't go there. Like, it's, you can't challenge certain narratives.
Well, the thing is that, I mean, if you wish, I've done the easy work. Because, okay, now that one has been convinced, and it doesn't take long to convince oneself that there was a conscious effort to replace one physical approach or one scientific approach with another scientific approach with different methods and different presuppositions and different specifically ideological presuppositions, or if you wish, different metaphysics. From there to actually going to read the articles from a technical perspective and to follow all the math and to figure out the experiments that validate or invalidate certain ideas and the kinds of experiments that would be necessary to distinguish these, and then to be able to publicize this and find the appropriate megaphone to make this widely known, because otherwise it just becomes 2-3 people working on their corner. They do interesting stuff, they die out, and it's as if they never did anything. So the point is that I did the easy stuff, but there's a lot of hard work to follow.
Thank you, John. Richard, I promised I'd circle back if we had a bit of time. We do have a little bit of time still left before 4. So if you had another pressing thought or question you wanted to toss out there, now would be your time.
Were you talking to me?
Yes, Mr. Moore. Yes, I
Oh,
know.
well,
I
thank
cut you off because I know you were asking another question, and
I didn't mean to take up too much time. I brought up longitudinal waves because that gives a mechanism for, for action at a distance, because, the speed at which you could go longitudinally
would be much faster.
Yeah. So,
Much,
I mean, it's like the metaphor is that you have a rope going up to a wall, and if you flip it, it takes a while for the wave to get there.
Yeah.
But if the rope is taut and you pull, I mean, you're pulling the same time you pull, you're pulling on the wall.
Right, and that might already give an explanation for some of the weird stuff in quantum mechanics. If essentially what that does is at least takes away from the straitjacket of 3 times 10 to the 8 meters per second.
Yeah.
But it doesn't state whether, so suppose you have these longitudinal waves, they would still have some speed limit. But that might, and so the question is there a speed limit to the universe, or is it like the granos are suggesting that things are literally instantaneous?
How much
Are
faster
things
would it be?
happening? Are we talking about some astronomical speed, or are we talking at some infinite speed? So if we go back to the 17th century, they couldn't distinguish that for the speed of light, whether light was instantaneous or whether light was just very fast. Well, now we know that it's very fast, but it's still very slow in comparison to gravity. Okay, so is gravity instantaneous, or does it actually take place at a certain speed? We don't know. It's just that right now we have just like the 17th century people with respect to the speed of light, we have no idea how to distinguish instantaneous from ridiculously high, ridiculously fast speeds. We have no instruments. We have no idea how even we could possibly distinguish the two. So that's for future generations to figure out. Maybe they'll be able to figure out it's, I don't know, 25 quadrillion times faster than the speed of light. Exactly. But we have no idea. But it's a fascinating question. But it's certainly very fast, that's for sure. And longitudinal waves, I think, are most definitely exist, despite what Heaviside claimed. I think Ampere's work and the Peter Grano's work, I think, demonstrate that longitudinal waves definitely exist.
Just a quick question, approximately ballpark, how much faster would longitudinal waves be moving than typical light waves? Like just is there any measurability to this?
I don't know. I understand, but it's like
I think
trillions of time faster easily.
Yeah.
I mean, it seems instantaneous seems to be the only answer anybody has come up with,
Yeah. Or so fast that we can't possibly distinguish it from instantaneous.
Well, Wall had a model of gravity. I don't know whether it's right or not, but it's almost like a rope connecting the two bodies, because it's dipole effect within atoms.
Yes.
Yeah, and so the two dipole things meet, and it's almost like there's a rope connecting them. It's not even a wave.
So that would be consistent with the way the way Kepler describes gravitation in the introduction to the Astronomia Nova. He is insisting that the attraction is not to a mathematical point. The attraction is between something physical and something else that's physical. And if there was some weird shape, it wouldn't be to the center of the body. It would be to some part off to the side of the body. Well, that's very much consistent with Wall Thornhill's idea that it's the individual dipoles that are all interacting with each other.
Yeah, I mean, the calling it a point is just, integral calculus, gives you the same answer. I mean,
Yeah. But it's very important to distinguish when you're talking about mathematics and mathematical points and so on and so forth, and when you're talking about physics, which is about actual physical things.
Yep.
Thank you very much, everyone, for the
Yep.
interesting comments and questions. I very much appreciate having an audience, because this is sometimes you explore this stuff and it's like you need feedback.
Well, thank you for sharing your research so far, John. I'm looking forward to your continued exploration into Carnot and whether this was indeed done to Sidi Carnot and his network. So yeah, that'll be I think a good preview of a future class that is becoming slowly into reality. So thank you everyone for taking the Sunday. Thank you, John. Until next week.
Thank you, Matt.
Thank
Hasta
you.
luego.
Well done, gang.
Ciao.
Adios.
Thanks
Adios.
a lot. Very interesting.